So this video is in response to the fact that the part 2 video for section 10.1 and the video for 10.2 does not have any sound to it. So I'm basically just going to fill in what sound you guys missed. The notes are already written out here, so I'm just going to kind of discuss what was said on those videos that didn't come through. Okay. So before we look at the part 2 stuff, I want to look at the end of part 1 because that's important for us for moving into part 2. And what we ended part 1 with was talking about the conjugate base and conjugate acids. Okay, so these are, even though they look like it, they look like chemical reactions, but they are improper chemical equations. Okay, we just kind of wrote them that way so we could see how to write out the formulas for the conjugate base and the conjugate acid. Okay. What happens is when we are writing a full chemical equation of an acid or a base, we have to keep in mind that we have water present. Okay, remember, water has to be present in order for us to have an acid or a base characteristic. Okay, so what we did then was we looked at these different acids and bases interacting with water. Okay, so we started off with acetic acid. Okay, and we have, it's going to donate a proton because it's an acid. The proton that it's donating is the hydrogen that's out in front. Okay, any hydrogen out in front is an acidic proton. Any hydrogens that are listed in the middle of a formula are not acidic. These protons, these hydrogens here, can't be donated. So these are not acidic. So we only look at the hydrogens listed out in front. So acetic acid is going to donate or give up this proton. When it gives up the proton, it forms the conjugate base of C2H3O2 minus. Water, which is present in this equation, is our base. It's going to accept that proton. And when it accepts the proton, it forms H3O plus, our conjugate acid. In acid-base chemical equations, we're going to have two conjugate acid-base pairs. We're going to have our acid in with our conjugate base, and our base with our conjugate acid. Next example, we looked at the carbonate ion. Okay, this is going to act as a base. It can't be an acid because it doesn't have a proton out in front. So if it doesn't have a proton to donate, then it can't be an acid. What that is going to do if we have a base here is that's going to force water to be an acid. So water is going to donate a proton to form the conjugate base of the hydroxide ion. Then our base is going to accept the proton to form conjugate acid, which is HCO3 minus. Then we looked at sulfuric acid, this H2SO4. Sulfuric acid has two acidic protons, but when we look at chemical equations for acids and bases as they interact with water, we're only going to lose one hydrogen out in front. Okay, there are other types of reactions, which you'll get into in section 10.5, where all of those hydrogens will be involved. But when we're looking at it with water, we just look at one hydrogen at a time. Okay. So our acid donates one hydrogen to form our conjugate base, HSO4 minus. And water is, again, goes back to being a base, so it's going to accept the proton to form the conjugate acid of H3O plus. So these were just three examples of looking at the chemical equations for acids and bases. So our acids or bases interacting with water. One thing hopefully you've noticed is that water acted as a base in two of the examples, but acted as an acid in another. This property of being either an acid or a base, depending on what it's mixed with, is called amphoterism, which was covered in section 10.2. So that's just basically it can be either an acid or a base, depending on what it's paired with. So we saw water up in the examples up above. We may not have noticed it, but we did see this with HCO3 minus. Okay, if we go back to our conjugate acid and conjugate base notes, okay, our HCO3 minus we took as an acid. to write its conjugate base. In the conjugate acid example, we saw HCO3- as a base to form a conjugate acid. Okay, so amphoterism is not a unique property to water, but water is one of the more common things that can be an acid and base, and the effects of that or the implications of that are specifically discussed in section 10.3, where it talks about water is both an acid and a base. So looking at that sort of reaction is in 10.3. All right, so back to section 10.2. And the next thing we talked about was the strengths of acids and bases. There is a table in your book that lists the strong acids, the weak acids, strong bases, and weak bases. You do not need to know that. Okay, I want you to be able to identify the strengths of an acid or a base by their reaction arrow, just like you did for the strong and weak electrolytes. Okay, same rules apply. If you have the double reaction arrow, you're looking at a weak acid or a weak base. If you're looking at the single forward reaction arrow, you're looking at a strong acid or a strong base. If I don't give you a chemical equation, if say I'm asking you for a chemical equation, I would tell you in that problem, say I might ask you, write out a chemical equation for sulfuric acid in water. Sulfuric acid is a strong acid. Okay, and then you'd be looking at something like this. Most of the time you're going to see a equation or your arrows here to identify strong versus weak. Do keep the table handy from your book, especially when you're working through Q&P or when you're working with the Sapling online site, because the Sapling site and the Q&P will assume that you have that knowledge. So keep it handy just when you're working through those problems. But again, on an exam, I will give you that information. So then looking at our strengths, our first two examples here, our acetic acid and our carbonate ion, these were both weak. We had a weak acid and a weak base because we had our double reaction arrows. Sulfuric acid is a strong acid as indicated by the single forward reaction arrow. Now what's important for us for determining or distinguishing between a weak acid or a weak base and a strong acid or a strong base, okay, is because in a weak acid or a weak base, we have the double reaction arrow, which means we can have equilibrium. If we have equilibrium, that means we can have an equilibrium constant expression. So that was the last part of section 10.2. We looked at the equilibrium of carbonic acid. We have H2CO3 interacting with water, okay, to form our HCO3- and H3O+. Okay, so we had an equilibrium, so we can write out our equilibrium constant, a capital A. And all of our rules from Chapter 9 and all of our calculations from Chapter 9 still apply. So we're looking at our products over our reactants. So we had HCO3- times H3O+ divided by H2CO3. Water is not included because it's a liquid, and liquids and solids are left off. In Chapter 9, we had Kc. Okay, the C was from the concentrations, and typically we just looked at gases in Chapter 9. You may not have realized it, but we just looked at gases. So Kc is different than Ka, and that Ka just deals with an acid. Otherwise, the rules are all the same. Okay, there is an equilibrium constant called Kb, and that is an equilibrium constant for bases. Your book doesn't go into Kb, but on the Sapling site, it's possible that Kb is mentioned. Hopefully I've taken those out, but it is possible that Kb can show up from in some of those questions. The concept for Kb is the exact same as for Ka, except you would be looking at something accepting a proton rather than donating it. So that should wrap it up for these videos. Basically just giving you the video or the audio for part 2 for section 10.1 and the audio for section 10.2.